Okay, so we're going to start off by talking about the combined gas law, which if you look at the worksheet that you got in class last time, 11 through 14 deals with this law. So 11 is just asking you to write out the equations that we've looked at so far. And I don't care if you write them in terms of K or in terms of like the ones and twos, but for example, Boyle's law says that P times V equals K, because they are inversely related to each other, pressure and volume. Charles' law says volume over temperature equals K. And then Gay-Lussac's law says that pressure divided by temperature equals K. So those last two represent direct relationships. Then if you combine them so that you have all three variables, pressure, volume, and temperature, into the same equation, essentially that's just saying if we only hold number of moles constant in, how do those three variables go together? Well, since both pressure and volume are directly related to temperature, basically I would just take Boyle's law, P times V, and just divide it by T because they're both directly related to temperature, and just say that P times V over T equals K. And then if I wanted to solve for an unknown, much like what we've done in the past with Boyle's law, Charles' law, and Gay-Lussac's law, I would just say that means that for a sample, as long as I'm not changing the number of moles, the initial pressure times the initial volume over the initial temperature, and then we change some things, they would all be equal to the final pressure times the final volume over the final Kelvin temperature. So we end up with that equation. So both of these are considered the combined gas law. And then if I were to say it in words, it would just be pressure is inversely related to volume, but they're both directly related to temperature. So let's do a problem. So number 14, you were supposed to do a balloon has a volume of 2.45 liters at 22 degrees Celsius and 102 kPa. So that just basically is my V1, my T1, but I do have to remember to convert it to kelvins, and my P1, and then I have my T2, again I have to make sure to convert it to kelvins, and my V2. So we're just looking for P2. So P2 equals question mark. So if you haven't done so already, see if you can set that up and solve for P2. Okay, so there's my answer, 96.6 kPa. Always good to do a mental check, although it's a little bit tougher to really definitively say whether this answer is right just with a mental check. But let's do it anyway. The pressure is the pressure is dropping from 102 to 96.6 a little bit. Is that consistent with the volume dropping from 2.45 to 2.35? Well, no, it's not. Usually when volume drops, pressure goes up, but the temperature is also dropping. So because the temperature is dropping, we would expect the pressure to drop. So we have sort of one variable telling us that the pressure should rise, the other telling us that it should fall, which is why these are a little bit tougher to predict. But at least we know that 96.6 kPa, which is not too far below the original pressure, is reasonable, since one variable was telling us that the pressure would rise and the other was telling us that the pressure would fall. Okay, so let's go ahead and try number 15, the weather balloon question, and we'll go ahead and see how you do. Okay, and there you have it. 0.998 atmospheres was my original pressure, which makes sense because that's pretty close to standard pressure, and we're at ground level in St. Louis, so very close to standard pressure should make sense. The pressure did drop as the balloon went up in the sky, and that would be consistent with a temperature drop, and also with the volume of the balloon increasing. So there we go. Okay, so the next new topic we're going to talk about is the ideal gas law. So far we've looked at pressure, volume, and temperature changing, but I've also mentioned that number of moles is another variable that we can measure for a gas sample. So if the combined gas law says that pressure and volume are inversely related and they're both directly related to temperature, and that if I So if I do my math, P times V over T, for a given sample where number of moles is remaining constant, I should always get the same answer, K, right? So what we're going to talk about is, okay, so where would N fit into the equation? If we're wanting to actually make N a variable, something measurable, something changeable, where would it fit into the equation? So let's think about it for a second. How would, for example, volume increase in a sample, let's say a balloon, if the number of moles increases? So you should have said that volume would increase as number of moles increases. And so that would put N, number of moles, into the bottom of the equation, meaning that volume and number of moles are directly related. If I have a balloon, it has a certain number of moles inside. The balloon's not tied off, so I blow into the balloon, increase the number of moles. That's going to increase the volume. So what we've just done here is we've included all four variables. And when we include all four variables, we don't have to hold anything constant. And what this gives us is an equation that will always give us the same answer, because we're not stipulating that anything has to be held constant. So for any sample of a gas, pressure times volume divided by number of moles times Kelvin temperature will always give me the same answer. Okay, so it doesn't stipulate that anything has to be held constant. For this reason, we don't use the lowercase k anymore. The lowercase k, remember earlier, with the combined gas law, Boyle's law, etc., signifies that if we hold these things constant, we always get the same answer. We've erased that stipulation, and now we're saying, since all four variables are present, that we always get this same answer every single time. And so we're going to use a new symbol, and that new symbol is capital R. And capital R is called the universal gas constant. And by the way, we're now into notes, so if you're not writing this down in your notes, you need to pause and start doing that. But the universal gas constant R is a true constant, meaning that it always gives you the same answer. And for that reason, we actually have totally universal constant constants that we can write down for R. So anytime we do P times V over N times T, we get the same answer, as long as our units are consistent. Now our unit for volume has to be in liters. Our unit for number of moles is simply moles, and as always, our unit for temperature is kelvins. Okay? The only thing that can change when we're measuring a gas sample from one measurement to the next would be pressure, because we have atmospheres, we have millimeters of mercury, we have kPa. And so what that means is the actual number that we get for R depends on the pressure unit. And so what I'm going to do is give you three different values. If my pressure is being measured in atmospheres, the answer that we will always get when we do P times V over N times T will be 0.0821 for R. And since all of those units are different, when I multiply P times V and divide by N times T, all of those units are in the unit for R. So, and temperature is measured in Kelvin. So we get this compound unit, atmospheres times liters over moles times kelvins. All right, if atmospheres is not my pressure unit, R is going to be a little different. If my pressure unit is kPa, well, 101.3 kPa is equal to 1 atmosphere, which means kPa are 101.3 times smaller than atmospheres, which means there'll always be a bigger number associated with kPa. And the R value that we get when our pressure value is kPa is going to be 8.31 kPa times liters over moles times kelvins. And then the last one would be millimeters of mercury, or torr. Remember, torr means the same thing as millimeters of mercury. And so if we're in one of those units, it's going to be even bigger, because remember, standard pressure in millimeters of mercury is 760. So 62.4 mmHg times liters over moles times kelvins. Okay, so those are my 3 R values. The other thing I want to say is we're generally not going to leave the equation in this form, P times V over N times T equals R. Instead, we're going to rearrange it, and it gives us the normal version of the ideal gas law that we're used to seeing where there's no fraction. So if we just multiply both sides by N times T, I get the ideal gas law that I'm used to seeing, that you will see, and that's PV equals nRT. So this is an equation that's going to be helpful for us in solving for any of those 4 unknowns. Remember that R is a known, it's a constant, so we'll never have to solve for R. Okay, let's try a problem. How many moles of N2 would the sample contain at 110 kPa, 24 degrees Celsius, and a volume of 36.5 liters? So this is literally just a matter of plugging stuff in the equation. So if I have PV equals nRT, we can rearrange. I like to rearrange usually. I can rearrange the equation to solve for moles, which is N, by dividing both sides by R times T. So that's going to give me N equals PV over RT, and I just plug in my numbers. So N equals, pressure is 110 kPa, volume is 36.5 liters, R, since we're in kPa, is going to be 8.31 kPa times liters over moles times kelvins. And yes, I do include that big long unit every time I write it. And my temperature is 24 degrees Celsius, which if I add 273 is 297 kelvins. And so let's go ahead and see what you get. Okay, there you go. So 1.63 moles. Notice everything canceled except for moles. kPa cancels, liters cancels, and kelvins cancel. And I didn't really use the fact that it was nitrogen for any purpose. If I had been asked to solve for the number of grams that this weighed, then that would be where the identity of nitrogen would allow me to convert it to grams using stoichiometry. Okay, let's try a new one. At what pressure would 0.054 moles of a gas occupy 24 milliliters at 62 degrees Celsius? What's the version of the ideal gas law that you need to solve this one? Okay, there you go. So P equals nRT over V, just divided both sides by V. Let's go ahead and plug in our variables and solve. Don't forget to convert your temperature, and the volume does matter. It needs to be in liters. Also, let's convert this let's solve this for pressure in atmospheres. So what pressure in ATM? Okay, and there you go, 62 atmospheres. Very high pressure, but we've got a very small volume, so that should kind of make sense for us. Okay, so here's another question. This one's a little bit tougher because it's asking for molar mass, and I want to give you a big hint that you want to pay attention to this one because it's going to be very similar to a lab that you do next time. What is the molar mass of a gas if 0.103 grams of it occupies 55 milliliters at 102 kPa and 22 degrees Celsius? The first thing we have to do is think about what is the definition of molar mass. So there you have it. Molar mass is the number of grams per mole of a sample. So if that's true, we're very close to figuring out the molar mass because we know the number of grams is 0.103. All we have to do is use the pressure, volume, and temperature to figure out the number of moles, which we should be able to do using the ideal gas law. So give it a try. So there's my moles, and if I divide grams by that, I should get my answer.